Hello everyone. I'm going to try to be as fast as I can. My name is Fatima. I am a graduate student at Marshall University here in Huntington, West Virginia. And I'm just going to be, this was my thesis, and I'm just presenting it to you all. I hope you find it fun. So I was working on graph theory. It's like a combination of graph theory and algebra, because we used most of our work from algebra to just make our works a lot easier. So this was like our background work. This was like an 1800s problem, and it's formed like one of the genesis of why we study, you know, why we study Hamilton cycle decompositions. Okay. It's just a problem of you having an odd number of people and you want to serve them and different dinners at a round table so that nobody sits next, like you don't want people talking to the same person more than once. So this is for like a 7 people. And we found out that that was actually just you decomposing the complete graph K7 into 3 Hamilton cycles. So I'm going to, in a way, just brush through this. A Hamilton cycle is just a collection of edges that creates a cycle using every vertex. So you just see, like I'm using all the vertices, I'm not repeating them in any way. And a decomposition is just us taking all the edges of our graph and partitioning it into Hamilton cycles. So you don't want so okay, so let's come back to this. Oh, I think I have an example here. Good. So this is the complete graph K7, and this is like us taking all of its edges and partitioning it so that no two graph uses the same edges more than once. Okay. And so we use a variation of the Cayley graph, and this is just a quick definition. It says if you have a graph on V vertices, then just label its vertices with ZV, and you have something called an edge length between two vertices. If you just take 0, 4 and subtract, just find your difference, and it goes both ways. If I do 0, 4 and I do 4, 0, so that's like why I have like a plus or minus right here. So if I do 0, 1, that's a 1 minus 0, that's 1. And if I do 1, 0, that's 0 minus 1, and that's minus 1. So this is a Cayley graph that contains two edge lengths. That's the word we use for just to call this kind of thing. And it's denoted by just X, number of vertices, and this is the set of edge lengths. So all of this will be important in a minute. And so we concentrated on the complete multipartite graph, Kn by n. I'll just use a picture to make that a lot easier. It's just you have m parts, but all of size n. So this is K3 by 5 is 3 parts, all of size 5. So its Cayley graph notation is this. So 3 by 5 is going to be 15 vertices. So just put that in, a cycle and just connect all of the edges in different parts. So there is there's no edge between 0 and 3 because they're in the same part. There's no edge between, 1 and 4 because they're in the same part. So you can't have an edge between them. So that's what a complete multipartite graph is. It's like just the older version of bipartite graphs. Okay, so we looked at two structures. The first structure is, and I'm sorry if I'm too fast. I just wanted us to get to the fun stuff, but we need all of those introductions before we get there. Okay, so we have that a decomposition. So remember I said a Hamilton cycle decomposition is just you taking a graph and decomposing it into Hamilton cycles. Well, it is cyclic if you apply sigma. So sigma here is a permutation that just adds 1 to a vertex. So if you take, sigma and act it to a cycle, you get back another cycle in your set of cycles. So a decomposition is just a set of cycles. So imagine And this has to happen for all of the cycles in your decomposition. So that's when you have a cyclic decomposition. So let me just take this one for example. If I act sigma to like this cycle, well, I have an edge going from 0 to, now I will have an edge going from like 0 plus 1, 1, and 2 plus 1, 3. So that's going 1, 3. But that is not in here, it is in here. So you see, even if I apply sigma to this, I still get another cycle in my Hamilton cycle decomposition, okay? So another structure we looked at was symmetry. And so this one is kind of like, to some extent, very vague. A cycle itself is n-symmetric. If you apply sigma to it, v over n times. So in this case, it was like k 3 by 5. So v is 15. And n in this case would be 5, because in actuality, I have to apply sigma to this 3 times to get back my cycle that I started with. So if I do sigma once, I get an edge going from 1 to 3. If I do sigma again, I get an edge going from 2 to 4. If I do sigma a third time, I get an edge going from 3 to 5. So now I'm back to my cycle. So, and it's also 5 symmetric. This is also another graph. It is 15 symmetric because, well, if I apply sigma to this, I just get 1, 5. Well, it is the same cycle. So that's just 15 over 15. So it's 15 symmetric. So 15 over 1, and it's 15 symmetric. It's also 5 symmetric because, well, if I just do this 5 times, I still get back the cycle I started with. So it's also 5 symmetric. And then you just say that a decomposition is n-symmetric if, well, everyone in there is 5 symmetric. Well, in this case, it's 5 symmetric. So now let's get to the fun part. To be able to decompose our graphs, because we're talking about multipartite graphs, you can have really weird, graphs. You can have like K51 by, 105. How can you make your work a whole lot easier? This was like by Baratti in some earlier years. He introduced this notion of base path, and it just uses all of this condition. So if you have a path in your graph that, just go from 0 to this, and then it ends at AD, then it is a base path if and only if it satisfies all of those conditions. So the first condition is everyone has to be distinct mod D. The next condition is your last vertex, which is AD, has to be a divisor of D. Oh, sorry, D has to divide it, meaning it's like 0 mod D. And all of the edge lengths that I use in here. So what are edge lengths again? Remember, I said it's just A1 minus 0, A2 minus A1, AD minus D minus 1. So all of those edge lengths has to be distinct, and the order of my last vertex has to be V over D in ZV. So we will see like examples of that. And we say a set of base path is valid if the edge lengths used by the base path partition A. I think someone is saying something.
Yeah, just 15, maybe take like a few minutes because we have to get to the next talk.
I understand.
In order to make the keynote. Yeah, just let it, just 2 to 3 more minutes. Yeah.
Okay, so I'll just move to the actual part. And we were able to just do this because, okay, good. So this is where I was coming to. So if I have a base path, I'm trying to create, so I have a base path, how can I get a decomposition, or how can I get a Hamilton cycle, so to say? So if I have the base path 0, 2, 1, 6, I just have to apply sigma to that. If I apply sigma to it, I get this part. Like this is just the same thing, 0, 2, 1, 6. And then the next, and then just keep applying sigma to that, repeatedly, and then you get 3 cycles. Remember, this looks like all the cycles in K3 by 5. And this are the base path of length 1 because they only use 1 edge length. So if I apply sigma to that also, a number of times, I get back my cycles. So in general, you can just use base path to find your correspond. You can just use basebats to find your cycles. And so the rest is just our work. So the main work was, this was just why we can't use basebat of length 1. You can just use that. There was a reason why. But this was our main result, that every Kp by n, where P is odd and n is also odd, has a cyclic decomposition. And every Km by n, where it satisfies these conditions, is also has a symmetric Hamilton cycle decomposition. And this was how we just went about our proof. And I think I can just take questions at this time. I hope you all enjoyed that, and I really apologize for my tardiness. Okay.
Yeah, thank you, Fatima. If there are any quick questions, maybe we could take one question. And let's also thank our speaker.
Thank you all.
Hey, Fatima, is this written up anywhere that we could go to try to read more about it, since you had to go quickly?
Okay, I could share this. That's one, because like I said, it's my thesis. We haven't worked on getting the paper published yet.
Okay, yeah. Or if you could share the PowerPoint or something, because it's interesting, but I need more time to digest it.
Thank you. I can totally do that. So I can just put it in the chat, and I hope I'm able to share. Oh, I see files. Okay, I'm able to share it. Well, I'm glad you guys enjoyed it. Thank you so much. Thank you. All right, I will post it. Thank you.
Yeah, let's thank our speaker again.